How does maneuvering speed depend on weight? The design maneuvering speed is the speed at which the airplane will stall before exceeding its design limit load factor in turbulent conditions or when the flight controls are suddenly and fully deflected in flight. The maneuvering speed is always published for the max gross weight, but this formula can help you determine the maneuvering speed for any weight. And in general, if you know the maneuvering speed V0 for a specific weight M0, then you can find the maneuvering speed V1 for a specific weight M1. And you can see that if the airplane's weight decreases, its maneuvering speed decreases as well. Let's talk about why it happens. Well, first of all, Newton's first law of motion states that a body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by a force. In other words, in straight and level flight, all forces are balanced. The force of lift is equal weight and thrust is equal to drag. And the total force equals zero. And the example of that would be when the airplane is motionless on the ground or flying at a constant speed in a straight line in a level flight, also during a constant speed climb or a constant speed descent while flying in a straight line. However, if there is a force that, an extra force that acts upon the airplane, then the airplane will change its speed or the direction of motion. For example, if we deflect the flight controls, we increase the force of lift and it's not equal to weight anymore, and the airplane will start climbing. And the important part is not just it will be climbing at constant speed, but it will accelerate. Its climb rate will increase from 0 to some value. The same thing happens in turbulence when the change in wind speed or wind direction can increase the force of lift and the airplane will climb. Also, if the airplane weight suddenly changes, then the lift becomes more than weight and the airplane will climb as well. Even though we don't have real control over the airplane weight, meaning that we cannot change it immediately to what we want, nevertheless, the weight changes continuously as we fly because we burn fuel. Now let's do some math. Well, first of all, let's look at this airplane, which is in a straight and level flight. And let's look at the projection of all the forces on the vertical axis. And let's select that the force or acceleration pointing up is positive and pointing down is negative. In this case, our total force can be written like that. And we can also move everything containing weight to one side. And we can say that the total acceleration that the airplane experiences can be described as n g units, where n is the load factor and g is the acceleration in the free fall. And I will not go through the whole process, but I want to point out several things. That the load factor is actually equal to the force of lift divided by weight. That if we look at how the force of lift depends on other factors, we can see that it's linearly dependent on the coefficient of lift, which includes the angle of attack. And it also depends on true airspeed. However, we used to use indicated airspeed, and even though we cannot modify this formula to use indicated airspeed since it's dependent on the airplane and also other factors, we can substitute it with calibrated airspeed, which is very close to indicated. And what we will use is that true airspeed is equal to square root from the air density at sea level in the international standard atmosphere divided by the actual air density multiplied by equivalent airspeed. And equivalent airspeed is the calibrated airspeed adjusted for the compressibility of the air. And at the Mach numbers that we fly, the equivalent airspeed is pretty much equal to the calibrated airspeed. So in the end, if we do all the math, then we will get the formula that I have shown already. So now let's look at why heavy airplane has higher maneuvering speed. So let's look at those two airplanes. One is heavy and one is light. Both fly at the same airspeed, which is the maneuvering speed for the heavy airplane. If we deflect the controls, then at some point we will start increasing the angle of attack, and at some point the airplane will stall. However, it will happen before it will exceed its maximum load factor. If we start pulling on the yoke in the light airplane, then of course at some point it will stall as well. However, it will exceed its maximum load factor before the stall. So why is that? Well, first of all, as we know that the lift depends on the airspeed and on the angle of attack, which is in the coefficient of lift. When the airplane is heavier, then it needs more lift to offset for that heavy weight. So if both airplanes fly the same airspeed, that the heavy airplane has to fly at higher angle of attack. So it doesn't have as much angle of attack available, so the stall happens sooner. With the light airplane, we have much more angle of attack available, so the airplane will over-G before it will stall. Another way to look at it is that the load factor is equal to the force of lift divided by the weight. And again, if two airplanes fly at the same speed, at the same airspeed, and they have the same angle of attack, the maximum angle of attack that provides the maximum lift, then the lift force for both airplanes would be the same. However, the heavy airplane has more weight to offset that force of lift. And that's why heavy airplane can fly faster, and it will not exceed its load factor at the same airspeed as the light airplane. So let's look at the real world example. So this is a picture from a Cessna 172S POH, and it actually provides maneuvering speeds for 3 different weights. So if we'll use this formula, then we can see that the calculated maneuvering speeds for 2,200 pounds and 1,900 pounds are very close to the published ones. So you can see that this formula works. Another way this formula can be used is if we look at the POH for a Cessna 172M, which comes from the factory with a 160 horsepower engine, its maximum weight is 2,300 pounds. Maximum gross weight is 2,300 pounds, and the maneuvering speed at this weight is 112 miles per hour. However, we can replace the 160 horsepower engine with 180 horsepower engine, and the maximum gross weight of the airplane would increase to 2,550 pounds. So now we can use this formula to recalculate the maneuvering speed for the new maximum gross weight, and that would be equal to 118 miles per hour. However, if we convert the miles per hour to knots and use the formula again, that our maneuvering speed at the maximum gross weight would be 102 knots, which is exactly the same maneuvering speed for the maximum gross weight of 2,550 pounds for Cessna 172S, which comes from the factory with 180 horsepower engine. And that is because even though they replaced the engine, the airframe remain unchanged. However, disclaimer that this number should not be used as a new limitation. If your STC doesn't specify a new maneuvering speed, you should use the number from the POH. Thank you for watching.